For the next talk, we have a recorded remote talk from Josselin. Yeah. And for questions, we have one of the authors here in person.
Hello everyone, thanks for having me. My name is Josselin Poiret. I'm a PhD student at Gaetan in Nantes, working mostly on rock and proof assistance. And today I'm going to talk about our recent paper on sort polymorphism, which is a newish feature that we're still trying to improve step by step. So first I'm going to maybe introduce the problem that sort polymorphism is trying to solve, and then we're going to focus on the chosen solution, which is prenex quantification in our case. Then maybe we'll talk a bit about our efforts to write a new sort polymorphic prelude that makes use of those new features, and then maybe talk a bit more about the theoretical work that we did on this sort polymorphic system before concluding. So maybe to refresh your memories a bit about proof assistance, I'm going to talk about mostly rock, but also a bit of lean and Agda. So those proof assistants let us formalize mathematical reasoning using something called the propositions as types paradigm. So that means that we consider types to be propositions. And here, for example, you can see that I've written the basic tautology, which is that A implies A for any proposition A. And notice here that I'm quantifying over A in type. But quickly, users realize that we might benefit from having a finer notion of type because some types are better than others in some cases. So, for example, propositions, we should be able to erase them in extracted code because we don't want to manipulate complicated termination proofs, for example, when we just want to compute in the end. So that led to the addition of prop, and so types in prop are erased in extracted code. And also we might want to have something called strict propositions, which in rock is represented by S-prop this time, or just prop in lean and Agda. So strict propositions, they're propositions whose proofs are all equal. So that means that we don't have to worry anymore about having proven some proposition in two different ways. The system is just going to regard them as equal. But of course, with power comes great responsibility, and eliminating from prop and S-prop to type is more restricted than usual. So for example, if you want to eliminate an inductive from prop, you need to have it follow singleton elimination. And if you want to eliminate an inductive in S-prop, well, it has to be the empty type. You cannot eliminate anything else. And so now you can see that we have three different universes, type, prop, and S-prop. And you might want to have an identity function for them. But for now, what I can do is only write a duplicate definition for prop and for S-prop. And that quickly gets a bit unwieldy and requires a lot of boilerplates. So maybe a more involved example is that of binary products. So in rock, as of now, in the prelude, there is a distinction between and prop, which are just the binary products for propositions and for types. So as you can see, they're exactly the same definitions, where we just substitute prop for type. So that leads to a lot of duplication, lots of lemmas need to be proven for both of these, and they're just the same. So this is really unwieldy, and it's kind of unreasonable to keep adding new sorts if we're not going to make them more usable and more user-friendly. So lean actually does have some solution to this, but it's only a partial solution. Prop and type in lean are just synonyms for a single universe hierarchy. So prop is just sort 0 and type u is just sort u plus 1. So for example, in this way you can quantify over A in sort u to define the identity function, and this would work with both prop and type. So as you can see here, I can apply the identity function to true and nat. But this technique doesn't really work if I want to introduce the binary products, for example, because of those elimination restrictions I talked about earlier. And Lean really relies on eliminators to do its work. And so here it just throws out an error because it can't just derive a most generic eliminator. And also that solution doesn't really scale with newer sorts. Here it works because prop is impredicative in Lean, so you can just add it at the beginning of the universe hierarchy, but this wouldn't work with another predicative hierarchy, for example. So instead, what we chose to do was use something that was already present in Rock for some other reason, which is pre-next quantification for definitions. So this already exists for universe polymorphism in Coq. So for example, you can quantify over a universe level in the definition. So here I'm defining again the identity function ID, but it binds a universe level U that it's going to reuse to quantify over all types A of level U. And we're going to reuse the same system by introducing pre-next quantification by a sort variable this time, so S here. And we're going to bind S and U and quantify over all types of sort S and level U, and still give the same definition of ID. So here S stands for one of the three ground sorts, which are prop, type, and S-prop. And as you can see here, I can instantiate ID to make it work with true, which is in prop, and with nat, which is in type. And of course, the elaborator just lets us write ID of true. It can infer the proper sort here. And for the case of binary products, we can generalize them very heavily. So here I'm binding S, S prime, and S second. And as you can see, I can take a type of sort S, another type of sort S prime, and make a binary product at sort S second. So this generalizes and prod, but also a product of two types in S-prop that lands in type, for example, or just two types in S-prop that stays in S-prop. So this is very general. But of course, we have to follow the elimination restrictions I mentioned earlier. So suppose for now that we define sort polymorphic booleans. So they're booleans that live at a sort S, so I can instantiate them at type and I get the usual booleans, but I can also make them live at prop or S-prop. Then what I can do is I can always eliminate from a variable sort S to itself. So for example, here I can eliminate the booleans at S to the booleans at S and define the negation. I just match on the boolean and return the opposite boolean. But I cannot eliminate from a variable sort S to another completely unrelated sort. So for example, a ground sort like type. So here, suppose I'm trying to define a function that takes a boolean at sort S and gives me the exact same boolean at type. Well, I could try to do it by matching on the boolean and then returning the exact same constructor, but Coq is going to complain because I'm not allowed to eliminate from S into type. Because of course, if this definition was valid, instantiating it at prop or S-prop would give me something that is actually incompatible with the elimination requirements of prop and S-prop. And there is a very significant example of this, which is that of universes. Because universes, they all live at the sort type. So for example, prop is in type, S-prop is also in type, and type itself is in type, but at a higher universe level, of course. But that means that we can't eliminate something which lives at a sort S to its own universe. And you might know that because of its name, large elimination. And you might also know that it's the main ingredient to show that true is different from false. So that means that we can't show that true is different from false at a variable sort S. But it does actually work in our favor because true is actually equal to false in S-prop because strict propositions, all the terms of a strict proposition are equal. So this is actually fine and expected. So now all these features, they've been in Coq for quite a while now, but we haven't really seen a lot of adoption of those features. And one of the main culprits is that the prelude and the standard tactics, they both don't really support sort polymorphism. So for example, the prelude doesn't have the generic prod, for example. It only has and prod. And the standard tactics, they usually choke on anything that uses sort polymorphism. It's a bit of a chicken and egg problem. So we thought we could remedy this by writing a new prelude that uses universe and sort polymorphism. That way we'd also fix the tactics as we go. So that's exactly what we did for the paper. We have, for example, sort polymorphic lists. So it just takes a type at sort S and gives you a new type at sort S. And with that new prelude, we thought we'd try to target some higher level stuff. So one of our initial targets that we highlight in the paper is that of the setoid rewrite tactic, because it contains some Gaetan code and also some ML code. So the setoid rewrite tactic, if you don't know, is kind of like rewrite. It lets you replace terms in goals using some user-provided relations, not just the equality relation. But those relations, they might be in prop or they might be in type. And we might want to rewrite both of these, using both of these. So that meant that for setoid rewrites, the Gaetan definitions were completely duplicated for prop and type value relations, which was kind of a nightmare to maintain. And with the introduction of sprop, no one bothered to actually add them to the setoid rewrite tactic. So there's nothing for sprop. So what we did is port all of this to a single copy that uses the sort polymorphic prelude, and that way we also support sprop for free. So this was actually a nice success that we got pretty early on. And maybe now we could turn to the more theoretical side. So our system that we call sort poly that we introduced in the paper, we tried to make it compatible with Agda and Lean as well as Rock, because you might want to be able to benefit from this in other proof assistants as well. What we did in the paper is study a couple of meta-theoretical properties. The main guiding principle that was used to inform our design of the system was that we should be able to monomorphize sort polymorphic terms back into terms with no sort polymorphism. So it does seem quite simple. Let me give you an example. For example, here the empty type that is sort polymorphic, so it leaves at a generic sort S. We can turn it into the empty types at prop type and sprop by just instantiating S with all possible values. So that's basically monomorphization. But this seemingly simple principle does give us a lot of power. For example, we know that sort poly is equiconsistent with the monomorphic system because we can just monomorphize back proofs of empty and we'd get a proof of empty in the monomorphic system. So this is really nice. And then later on in the paper, there's also a definition of a parametricity translation for sort quantification, which roughly means that if you have a sort polymorphic function, then what it does at different sorts is actually the same thing. So this is basically parametricity, but for a new kind of quantification. So in conclusion, what we hope with this paper is that we'll be able to, in the end, integrate the new sort polymorphic prelude so that users can enjoy better usability. Learning with Rock should probably be easier, but also that experienced library writers would be able to write less boilerplate. But also from the more theoretical side, we're hoping that implementers will be able to add new sorts to their language using our system sort poly as a backbone. That way they'll be able to focus only on the interesting features of the new sorts they're trying to add. And as an example, we outline a couple of them in the paper, but we have exceptional type theory, but also type theory with ghosts, which is basically a refinement of the erasure property of prop in rock. So thank you for your attention. Thank you for having me. And I think Nicolas is in the audience to take your questions. Thank you again.
Your microphone? Okay.
Yeah, I think it's gone. It's okay.
Yeah. We can take questions. We have some time.
Does the sort polymorphism affect like performance, like type inference or anything like that? Like if the whole standard library is now using
so
this?
for elaboration, for example, it improves the elaboration because in previous system, when you elaborate and you just define A and you don't say whether it's type or prop, the system tries to guess for you, and at some point it has to make decision. Sometimes a bit too early, and it ends up in error in type checking. Whereas now you can keep a variable and say I will wait as much as I can to elaborate and type check my term. So now we have an expression in Rock that does type check now, even with just using prop and type that were not type checking before. So elaboration is improved. And with respect to performance, because there is already universe level attached to the universe, adding a new part, a couple instead of just one record, doesn't change much.
Any other questions? Yes.
Okay, so this theoretical framework of sorts, can that be instantiated with an arbitrary sort theory, and sort of what's the data of a sort theory then?
So you can postulate new sorts as axioms, and then you can add axioms on that sometimes exist in this new sort and so on. So you could define some part of model type theory this way. Simple one, the one where the substitution is valid in the theory. And then because we have added also rewrite rules in Rock, you can also postulate computation in your new sort if you want to kind of maybe prototype a bit. We don't pretend that it will be a definitive answer to the extension of the proof assistant, but at least for prototyping, it's very easy because you just open a section, postulate a new sort and new rewrite rule on it, and you kind of have a new proof assistant.
You also need to specify which sorts can be eliminated into other sorts, don't you?
Sorry?
You need to specify how you can eliminate from one sort to another
so
sort.
For elimination, we need to do a bit some work because we realized by doing the new prelude that being able to abstractly postulate the elimination from one sort to another will be very useful as well. So in the graph, for the moment, we already have a graph of dependency of constraint between universe level, and we want to add a graph of constraint of elimination between sorts that will be used to be even more generic, and this way we could postulate elimination. But it has not been implemented. It's for future work, hopefully soon.
Okay, there's someone else with a question? Yeah.
Hey, sorry if this is a silly question, but why would a term not be monomorphizable?
Sorry?
Why would a term not be monomorphizable? You said in the presentation,
yeah,
you said, we require that we can always monomorphize.
You mean how this theorem is not completely trivial? That's the question?
I thought that was a constraint you had.
Yeah, it's a constraint of somehow the elaboration of the system and all the elimination rules that we impose at the level of abstract sort have been done in a way that the monomorphization theorem works. So somehow it's kind of intertwined. But it's the sanity check of the definition of the system is that this theorem holds somehow. Yeah.
We have time for one more question if there's someone with a burning question. Yes, okay.
Did you find that you were able to incrementally migrate towards the more polymorphic prelude, or did you find you had to do it all at once or it would fall apart?
So we are trying to do it incrementally. So we already split the standard library with the core library in Rock. It's a kind of recent change, so that the standard library is still kind of oblivious from sort poly, and the core library is now fully sort poly. And then we have definitions to instantiate on ground sorts, and the standard library will be a bit less sort polymorphic for the moment because we don't want to destroy everything at once. At least we try.
Let's thank the speaker and Nicolas once again.